All right, so welcome to Daily Problems 02. And this is a mixed set, so on our free response questions, the calculators will be allowed. On the multiple choice questions, no calculators. All right, so here we go. Seems we've lost, oh, here we go, okay. Question 1. Oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left in the well. That is, dy dt equals ky, where y is the amount of oil left in the well at any time t. So without continuing further, anytime we see this type of problem, so dy dt equals ky, or anytime we hear this type of problem, the rate proportional to the amount left, that should tell us right away that we're looking at some kind of exponential growth or decay. Okay? So right away we know exponential growth and decay. Initially, there were 1 million gallons of oil in the well. So when t equals 0, y equaled 1 million. Okay? And 6 years later, so when t equals 6, oh dear, the pen hates me already. T equals 6 years, y equaled 500,000, so half the amount. And it will be no longer profitable to pump oil when there are fewer than 50,000 gallons remaining. So when y equals 50,000, I don't know why I put a comma in this one and not the others, then it's time to shut down. Okay? All right. Time is up. All right. So write an equation for y, the amount of oil remaining in the well at any time t. Okay? So here we go. So we start with dy dt equals ky. And you may be thinking to yourself, okay, this is exponential growth and decay, and every exponential growth and decay problem looks exactly the same. This is going to translate into some kind of y equals y0 e to the kt. We know this already. Why do we have to keep going? Why do we need to do anything else? The answer is they don't know how you know that. They don't know that you know the calculus. So you absolutely have to do the problem even though we know that you know this, okay? You must do the derivation every time if it's a free response. It sucks, but you got to do it, all right? So this is separation of variables. Separation of variables, you got to separate the variables. So we're going to divide by y, okay? Divide by y, and you're going to multiply by dt. Right? And so dt cancels on this side, and y cancels on this side, and you're going to end up with, I'm going to move over here, moving over here, we're going to end up with dy over y equals k dt. Right? And dy over y, that gives us natural log of the absolute value of y. Sorry, we're going to integrate. I should mention that. We're going to integrate. And then this gives us natural log of the absolute value of y. And on this side, we get k, because k is just a constant that stays there. And the integral of dt is just t. And we need a plus c. And we don't need a plus c on this side, because a plus c over here, we could just subtract it over here, and we'd get a different constant. So we don't need to worry about it. Right? And you don't need to write that. They're reasonably intelligent. They can figure that part out. Raise both sides to the power of e, and those guys cancel. And then you do need to make a quick comment that e, anything raised to the power of e, is always greater than 0. Oopsie. Having some pen troubles today. Always greater than 0. And so you can drop the absolute value at that point, right? So we can say that y equals e to the kt plus c. And remember, oh, the pen doesn't like me at all. Okay, and so at that point, remember that once upon a time, in our algebra classes, they told us that anytime you had a to the m times a to the n, that was equal to a to the m plus n, right? So we can apply that backwards. So if I have a to the m plus n, that's a to the m times a to the n. And so I can make this, not a, I really liked a all of a sudden. Let's see if it lets me erase that. There we go. And so that's going to give me e to the kt times e to the c. But c is just a constant. It's any constant, and we don't know what it is, so I can just change that into e to a constant is just another constant. So I'm going to change that into, and I'm going to move it in front, because we like our constants usually in front of our variables. So I'm going to have a new constant c1, e to the kt. Right? And so there's our function. It's kind of way back here, right? So I've got that y equals c1 e to the kt. But I'm not quite done yet, right? I need to figure out what c1 is. And I need to figure out what k is. So I know that at time t equals 0, y equals 1 million. So I'm going to take that, and I'm going to plug that in right here. So I'm going to say that 1 million, make sure I have enough zeros there, equals c1 e to the, and k times 0 would be 0. And e to the 0 is 1, right? So I'm going to have c1 times 1, which is c1. So c1 equals 1 million, right? So my new function is y equals 1 million, right? E to the kt. So I figured that much out, right? Okay, so we're doing all right so far. And then my second piece of information tells us that t equals 6 when y equals 500,000. So we can plug that in. So I'm going to have 500,000 equals 1 million e to the k times 6. And I'm going to divide by 1 million and divide by 1 million. And these guys are going to cancel, and I'm going to get 1/2 equals e to the 6k. And then I'm going to take the natural log. And these guys are going to cancel. And then I'm going to divide by 6, right? So I'm going to have the natural log of 1/2 equals 6k. Divide by 6. K equals the natural log of 1/2 divided by 6. So I can put all that together to get my final answer. Y equals 1 million e to the natural log of 1/2 divided by 6 t. It's a bit of a mouthful there. Okay? All right. And there's a final answer. And I have a funny feeling I might need this a little bit later. So I'm going to take a picture of that so that we can use it in a few moments. Partially because I would love to say that I'm going to remember what that is when I want to use it, but I have a funny feeling that I'm not. So just going to keep that for future reference. Okay? Okay. At what rate is the amount of oil in the well decreasing when there are 600,000 gallons of oil remaining? Okay, so at what rate? So if they're asking what rate, they're asking us to find dy dt. Is the amount of oil in the well decreasing when there are 600 gallons of oil. So 600 gallons of oil, that's not T, that's actually Y. So dy dt equals blank when Y equals 600,000, right? And if you're not sure, just look at the units, right? So Y is the amount of oil, and they'll tell you, right? We've been using that for gallons, right? This is in gallons. Time, right, would be in years, not in gallons. Okay, so at what rate dy dt when y equals 600,000? Well, you may be tempted, right? We usually think of dy dt. You may be tempted to say, well, here's my function for y. You may be tempted to go ahead and take the derivative and then, plug some things in. But that's far too much effort. We know what dy dt is. Dy dt is k times y. And we know what k is. K is, from the last problem, I can see it right here, natural log of 1/2 divided by 6, right? And y, they tell us, is 600,000, right? Nothing to it but to do it. I'm going to do a little bit of canceling because I'm a slightly lazy person. I'm going to take the 6 here and the 6 here and make this 100,000. Okay, be careful, you can't usually do that, but I'm feeling lazy. I don't feel like writing that out. And at this point, it's a calculator problem, right? This is k, this is y. Thankfully, I have a handy-dandy calculator for this sort of thing. Let's see. So we're going to have the natural log of 1/2, or 0.5, times 100,000. To be very careful, this, yes, we don't care about the malware. Okay, so 100,000, and we hit enter. 69,314.718. Okay, and that's it, right? Making sure I write this down here so that I can get it onto the next slide. Okay. Oh, it doesn't like me. Here we go. And then that's it, right? So this equals negative 69,314.718. We always remember 3 decimal places. Now be very careful. Dy dt equals a negative number. That should make sense because the amount of oil in the well is decreasing. But when you write it out, you want to make sure that this part is negative, but that your answer is not negative, because they asked you how much the amount of oil in the well is decreasing. It is not decreasing by a negative number, right? If it were decreasing by a negative number, that would be increasing. It's like the two wrongs don't make a right. In this, and it's like a double negative in English, right? If you say that, well, I ain't gonna, when you put two negatives together, it makes a positive. So you have to be careful. The oil in the well is decreasing at a rate of positive 69,314.718, and then units for this would be gallons per year. Okay? You need to be very, very careful how you write your answer to this. Okay? It's decreasing that much per year, but the derivative itself is negative. Okay? So So be very careful with this answer. Okay, and then finally, let me paste our function in here again one more time. Okay, in order to not lose money, at what time t should oil no longer be pumped from the well? So remember that it will be no longer profitable to pump oil from the well when there are fewer than 50,000 gallons remaining, right? So basically, they want to know, when will this be equal to 50,000 gallons, right? And at that point, that's when we stop. When it hits 50,000, that's when our profit margin stops. Okay, so easy peasy. We divide by 1 million. Right? This cancels. A bunch of these zeros cancel. And if I've done this correctly, I believe it comes out to 1/20th. So we have e to the natural log of 1/2 divided by 6. T equals 1/20th. We take the natural log, we take the natural log, these cancel. We get the natural log of 1/2 divided by 6. T equals the natural log of 1/20th. And then I'm going to multiply by 6. Multiply by 6. These will cancel. And then I'm going to divide by 1/2, or natural log of 1/2, sorry. And that should cancel, and that should cancel, and that'll give me t all by itself. You can feel free to leave it like this on a free response, or plug it into your calculator if you should so desire. I always, well, again, this is free response. You can feel free. I'm going to plug it in just so that we get some kind of idea of what we get here. So you're going to have the natural log of 1 divided by, okay, maybe not. The natural log of 1 divided by 20 times 6 divided by the natural log of 1 divided by 2, close parenthesis, enter, 25.931 or 932, because you can choose to round or you can choose to truncate. They won't care. So 25.932 years. Okay, so they can pump oil for a very long time. All right, so there's question 1. Question 2. A particle moves along the y-axis so that its velocity at any time t equals 0 is given by v of t equals t cosine t. At t equals 0, the position of the particle is y equals 3. For what values of t from 0 to 5 is the particle moving upward? So recall that whatever happens when v of t is greater than 0, the particle is moving upward. And you must say that so that they understand that you understand the calculus behind it. So when v of t is greater than 0, the particle is moving upward. Okay? So when is v of t greater than 0? Between t equals 0 and t equals 5. We can get the graph of this if we need the graph of this to help us out. And the graph may make our lives slightly easier. So we plug in x cosine x, and we set our window from 0 to 5, right? And graph. There we go. So we can see that it's going up and then down for a very long time, then it comes back up, right? So we know it's from here to somewhere around here, and then somewhere around here, right? And we can use trace to find these points. I think there's actually a much simpler way to do this. So let's come back to our point here. So, right? So like this, like that, and like this, right? So if t cosine t equals 0, I know that I can split these up, right? Similar to the way if I had two parentheses, right? Like, you know, t plus 1, t minus 2 equals 0. I could split those up to find out that t equals negative 1, t equals 2, right? So I can do the same thing with these guys. I can say this guy equals 0 and that guy equals 0. So where does t equal 0? Well, that one's pretty simple. That happens at t equals 0. And where does this guy equal 0? And where does this happen? Well, they'll probably happen when cosine equals 0. Where does cosine equal 0? Hopefully you guys remember your trig facts. This occurs at all of the pi over 2's, right? So this one is probably pi over 2. This one is probably at 3 pi over 2, right? So rather than struggle, oh, this is a 2, not a 3. So rather than trying to struggle with our second calculate and finding all those zeros, we can just use some basic trig to help us out, okay? So it's going to be, excuse me, so the particle is going to be moving upward between 0, right, and between 0 and pi over 2, and between 3 pi over 2 and 5, right? And I'm going to include 5 because it appears to still be upward at 5, right? All right, so that's when the particle is moving upward. And hopefully that makes some sense there. All right, part B. Write an expression for the acceleration of the particle in terms of t. Well, we know that the acceleration of the particle is equal to the derivative of the velocity. Easy enough. So, what's the derivative of t cosine t? Well, we've got product rule. So we're going to take the derivative of the first, that's going to be 1, times the second is cosine t, plus the first is t, derivative of the second is negative sine t, and that's it. And you can leave it that way. You don't need to simplify it. You don't need to make it look prettier. That's it. Okay? All right. Of course, if we wanted to make it look prettier, something like cosine t minus t sine t would be certainly acceptable. Okay? All right. Part C. Find the total distance that the particle has traveled between t equals 0 and t equals 5. So here they're asking for total distance, not displacement. So with total distance, we want to make sure that we're looking for, we want to make sure that we're using absolute value so that we're considering not just the distance between where it started and where it ended, but we're considering forwards, backwards, that kind of thing, right? Okay. So what we're going to do is we're going to take the integral between 0 and 5 of the absolute value of the velocity. Because the absolute value will allow us to consider the total distance, right? And you don't need to write more than this. You don't need to even put in cosine, t cosine t. You're just writing v of t, they'll understand that that means t cosine t. And this is a calculator problem, so we can go to our handy-dandy calculators to do it. Now, we've already put t cosine t in, so we can use that. So we're going to go to Oops. Let's get out of here. And I'm not in math print, so if you don't have a TI-84, this is how it works. So you're going to go to Math 9, which is FNINT. Then you're going to go to Math, and then switch over to Number. That's where absolute value is, and hit Enter. Then you're going to go to Vars, go over to YVars. That's where your functions are. Hit Enter. And there's Y1, so hit Enter. And so T cosine T is already programmed in for you, so you don't need to do it again. Comma X, comma, and then you're going from 0 to 5, so 0, comma, 5. And close your parentheses. Sorry. Bad Miss Bousquet. Miss Bousquet missed something in here, so that would have gotten her an error, because I missed the parenthesis for the absolute value. Right? So she closed the parenthesis here for the FNINT, but not the parenthesis for the absolute value. So I'm going to insert one. So I'm going to go to second insert, right? And then I'm going to put in a parenthesis right there, and that will put one in for my absolute value. Okay? And so now I'm going to hit Enter. And it's going to think for a moment. Apparently it's going to think for a long time. There we go. 7.005. Okay. All right. So 7.005. Sorry. Is it 7.055, not 005. So 7.055. Sorry about that. 055. Okay. And that's it. Part D. Okay. For t greater than 0, find the position of the particle the first time the velocity is 0. So we said that the first time the velocity was 0 was at pi over 2, right? I believe we said that in part A. So we're going to find the position of the particle the first time the velocity is 0, which is at pi over 2. So what we're going to do is we're going to say that we're going to look at how far the particle has moved between 0 and pi over 2. So remember that in part C we found total distance. That calculates how far the particle goes from here, and then maybe it moved backward a little bit, and then maybe it went this way, and then maybe it went this way, and it ended up here. And total distance calculates this plus this plus this plus this. When we find position, we don't want to consider it that way. What we're going to consider is only how far it went from here to there. We're going to consider just that distance, which is displacement. Okay? We only want to know the difference between where it started and where it ended. Because if we know that, then we can use this displacement, and then we can look at, well, if we know that displacement, we can then say, well, where did it start? Because if I can look at, well, I know on a number line that I started, right? If I know my starting position, and then I know my displacement, right? Then I also know my ending position. So your starting position plus your displacement is going to equal your ending position. Okay? So that's what we're going to do. Okay? So that's what we're going to do. And we know the starting position because we know the starting position is 3. Okay? So let's find the displacement. And the displacement is very similar. We're going to take the integral from 0 to pi over 2. And we're going to do that for v of t, but instead of using absolute value, we're just going to take the regular integral without the absolute value. Okay? All right. So we know how to do that. right? So we're going to go math 9, so that's FNINT, and then we're going to use y bars, and there's y1. But notice no absolute value because we're finding displacement. And we're going to go from 0 to pi divided by 2. And we get 0.571. Okay? So 0.571. And this, oopsie, this is our displacement. And then they tell us that y equals 3 is your initial. So your position will be 3 plus 0.571, better known as 3.571. It's nice when you don't need a calculator, right? And that's it. All right. Question 3. So now we're on to the multiple choice non-calculator questions. So which of the following is equal to the integral from 0 to pi of sine of x dx? So it might be tempting to actually try and find all these integrals and figure it out, but there's a much easier way. Remember that the integral is equal to the area under the curve. The integral, this integral here, right, if we draw a very rough picture, is equal to this area right here, right, from 0 to pi. So basically it's equal to one of these bumps here. Okay, so let's think about what each of these pictures looks like. So this first picture is negative pi over 2 to pi over 2 for cosine. So if I think about what cosine looks like, right, cosine starts here and goes down like this, that's pi over 2. And if I go backwards, it goes like that, right? Okay, very much drawn poorly to scale. So it's equal to one of these bumps, right? That seems to match quite well. So I'm liking A. Let's make sure none of the rest of them work. Okay? So the second one is going to be, well, let's think about what cosine looks like again. It starts up here, it goes down, right? That was pi over 2, and then it goes down some more, right? So it's actually going to cancel they're going to cancel each other out, and we're going to get 0. So that doesn't work. Okay. This one here, 0 to negative pi. So we're actually on this side. So sine starts here and goes up, so then it's going to go backwards, and it's going to be down here. So it's actually a negative hump, basically. So that's no good. Okay. Trying to come up with different colors here. This guy, that's almost the same color. Let's try a lighter one. This guy is going to be, starts up like this, right, and gets halfway for pi over 2, and then going the other way goes down like this, right? So they're going to cancel each other out, and that's no good. So that doesn't work. And then for the last one, let's try this pink color. For this guy, from pi to 2 pi, right? So this part is the part we like, but that's not the part that's getting colored in. It's going to be this part, right? So again, we've got a negative bump. That doesn't work. So the only one that works is A. Right? So that's number 3. Number 4, if dy dx equals 1 over x, then the average rate of change of y with respect to x on the closed interval from 1 to 4 is what? Okay, so we have to remember what average rate of change means. Average rate of change is not the derivative. Average rate of change was that secant line, right, where we find that f of x1 minus f of x2 over x1 minus x2, or in other words, it's the slope, right, using 2 points. So we've got to figure out how can I make this into something I can use, basically. Well, looking at this is essentially something I can take the integral of, right? This is something that, okay, I know that dy dx equals 1 over x. I multiply by dx. I take the integral. This is essentially y equals natural log of the absolute value of x plus c, essentially, right? I mean, looking at this, that's pretty standard, right? So, okay, let's take the average rate of change of natural log. So I'm going to plug in from 1 to 4, right? This isn't a point, this is an interval. So I'm going to plug in 1 to 4. Well, natural log of 4, right? I could do this starting at 1, but usually we start at the other point. So I'm going to say natural log of 4 plus c minus natural log of 1 plus c over 4 minus 1. And look what happens. This is going to become natural log of 4 plus c minus natural log of 1 minus c, and the c's are actually going to cancel. Which should make sense. It's the average rate of change. And this plus c, all it does is move the curve up or down a little bit. So the plus c's don't really matter. Over 4 minus 1. And the natural log of 1 is 0. And we get sorry, I'm not sure why I'm moving over here. And I get the natural log of 4 over 3. Wait a minute, I don't have that anywhere. But look at the two natural logs that I do have. I have natural log of 2 and natural log of 2. Can I make this into the natural log of 2? Yeah, I can. I could say that that's the natural log of 2 squared over 3. And then I could bring the 2 out front and make that 2 natural log of 2 over 3. And that is letter C. There you go. Not too bad, right? All right. And finally, number 5. If f of x equals x when x is less than 1, and 1 over x when x is greater than 1, then the integral from 0 to e of f of x dx equals what? All right. Well, I know that 0 to e spans more than 1, so that means I'm going to have to break up my integral. Right? My integral is being broken up. Poor integral. It's having a breakup. That's sad. So, I'm thinking of two integrals. One that goes from 0 to 1, and one that goes from 1 to e. Okay, and the integral that goes from 0 to 1, that's going to be this guy. Right? Because that's the integral that has 1 in it. Or that's less than 1, right? And this is the integral that's less than 1. So that's going to be the x dx integral, right? And then the other integral is bigger than 1, and this integral is bigger than 1, so this one's going to be from 1 over x dx. That's not so bad. And I know how to do this. The integral of x dx is 1/2 x squared, going from 0 to 1. And that's just going to be 1/2 times 1 squared is 1, and 0 squared is 0. 1 minus 0 is 1, so I'm going to get 1/2. then here, the integral of 1 over x dx is the natural log of the absolute value of x. And that's going from 1 to e. And the natural log of e minus the natural log of 1. And the natural log of e is 1. And the natural log of 1 is 0. And 1 minus 0 is 1. So I get 1/2 plus 1, which is 3/2, which is b. And there you have it. So hopefully that made sense, and if you have any questions, post them in Edmodo. Have a wonderful weekend, guys.